Next up, suppose a car presently worth $30,000 depreciates 20% per year. About how much will it be worth 3 years and 3 months from now? So it's a depreciation model. That's 1 minus R. It's 20% per year. So our R value is 0.2. Initial value here is 30,000, and our time, 3 years and 3 months, is 3.25 years, right? So we're going to start with our depreciation model. We're going to identify our key parameters, 30,000. R is not 20%, it's 0.2, and T is 3.25 years. And we're going to drop those values in. So it's 30,000 times 1 minus 0.2, which is 0.8, to the 3.25 years. And this is going to calculate to approximately $14,526 now. Last question. We have a table of values relating the time in minutes and the grams of some substance, right? So it says first it says write a function equation for A of t, and then it says approximate how many grams will remain after 1.25 hours. So I'm going to show you two methods here. The first method is going to be over here. And what I went and did is I looked at two consecutive values in the table. It's clearly an exponential growth, or it's an exponential decay model. So my first data point was 0, 400. My second data point was 10 to 84. And I'm going to set up a system of equations like we did in 5.31 lesson. So 400 equals AB to the 0. If you understand that this is a y-intercept just by the table, you know right away that the A value is 400, but B to the 0 is 1, giving us A is 400. Now we're going to take that value and substitute it into your other equation, which is 284 equals AB to the 10th. Again, we're modeling this all after the parent equation, y equals AB to the x. So once I substitute 400 into here, now I have to solve for B. So I'm going to divide both sides by 400. If you approximate this, that's totally fine. Just don't round too early. 4 decimal places is good. And then to solve for B, right, you're taking the 10th root of both sides. Now, 10 is an even number. This is an even index. Plus or minus would make sense in this case. However, in this particular example, we're solving for a B value. We always want it to be positive. We're going to leave B positive. So alternatively, you could take both sides to the 1/10th power, and that would produce the same value. B is approximately 0.9663. And then we're going to drop that into our equation. So y equals 400 times 0.9663 to the t power here, right? Question is just saying, let's go back to the question. Write a function. That was our function. Approximate how many grams will remain in 1.25 years. So, 1.25 years. What we're going to do is we're going to put 1.25 into t here, calculate it. It's going to be about 29.7 grams here. Now, if you go back up to the question and you're paying attention to the table without just jumping into a procedure, you can't notice it in your second data point here, but you definitely can notice it in your third data point, right? So you can see that this value dropped by half right away, in 20 minutes. And you can see also over here from 20 minutes to 40 minutes, that's another 20 minutes, it cut itself in half here, right? So we could turn around and look at this from a different perspective, right? So if it's cutting itself, if this amount of substance is decaying by half every 20 minutes, then we can say that the decay factor is 1/2. That's your B value. And we can say the unique interval of time right now is every 20 minutes. That would be your K value. So we can use this model here. A of t equals AB to the t over K. And then we know it's decaying by half. That's your B value. Every 20 minutes, that's your K value. And we can drop this information in. So you would end up with 400 equals 1/2 to the 20, to the t divided by 20 power. It'll be a different looking equation, but in the end, it'll give you the same exact value, 29.7 grams here, right? So if you use the second model here, these are two completely separate equations, but they're both equivalent equations, and they both produce the same values, right? Either one works. You're not going to have to use a specific one, but in some cases, you can avoid all this mathematical work and reduce potential errors if you recognize right here that it's decaying by about half every 20 minutes.